this video, I'm going to explain about a Peterson solution, which is the simplest solution for the critical section problem. In my previous video, I explained about what do you mean by critical section and what is the problem with the critical section. And whatever the processes, the processor are broadly categorized into two types. One is cooperative process and another one is an independent process. So cooperative processors are the processors which can share its data with other processors. And we in the entire the process synchronization thing, we are talking only about what? Cooperative process. So this cooperative process are the processors which can share its data with other processors, or it shares other data. That means there is something is shareable between the processes, and that processes we call in cooperative processes. What they can share? They can share either data or it may be the resources. A data may be a variable, or it may be some table or some database or some code, whatever. Okay, but resources means it may be a file, it may be input device, it may be output device, it may be a memory space, or it may be some buffer, or it may be a CPU. Okay, so these are the results. That means these cooperative processors are sharing the data or the resources that we in detail we discussed in the previous class. Okay, now what do you mean by critical section? Critical section is the part of the program. So in every program, we have some set of instructions. Out of this instruction, there are some instructions are there. They are non-shareable. That also we discussed in the last video. Okay, non-shareable. That means these are the private statements of that particular program. That means these statements are not shared with anyone. Okay, or nobody is sharing this one. Okay, now another section will be there. This is our shared part of the program. That shared part of the program, it may be a data or it may be a resources, and this shared part of the program we call it as what? Critical section. So what is the problem? So when more than one process are in this critical section, so then it may be leads to data inconsistency. That also we discussed in the last video with many examples. Okay, now that means the shared data can be accessed by out of any one process at a time. See, when one process is using this shared data, we should not allow other processes. That is what. Okay, now, so this is the problem. Okay, so to avoid data inconsistency, or we can say in other words, to make data consistent. Okay, so we have to make some solutions so it should not suffer with the critical section problem. Okay, so any solution which gives some method which gives solution to solve this critical section problem, there has to make these three requirements. They have to satisfy these three requirements. Those are mutual exclusion, progress, and bounded waiting. Among these three, these two are mandatory and this is optional. Okay, and what is this mutual exclusion, progress, bounded waiting? That also we discussed in the last video. If you not watched my last video, or if you don't know this concept, please watch the last video and then come to this one. Okay, now in this video I am going to explain how this Peterson solution is used to solve the critical section problem or the trace conditions. That means whenever more than one processes are in the race to access the shared data, or we can say to access the critical section, how to avoid that, okay, that. So any process, any cooperative process, the general structure of any cooperative process will be like this. Okay, now it will have some entry section, some code will be there. Now this is my critical section, that is, this is my shared data, okay, or resources. Now this is my critical section, and we should allow only one process at the same time. So now any process wants to enter into the critical section, first they need to check if somebody else already is there or not. If no one is there, then only we need to allow. So that checking part will be done in this part, intersection. Now any process after completing its critical section, once they come out, they should give the chance to some other. So that is what the progress, and for that it will exit section, and the remaining section, remainder section means this is a non-shareable. That's what the non-shareable. Okay, so now this is the general structure of any cooperative process. Okay, so now The Peterson solution is one of the simplest solution for the critical section problem. Now let us see how this solution will implement the entry section and exit section. That means now the concept is how Peterson solution is allow only one process to enter into the critical section at the same time. Okay, that's what the Peterson solution. And any solution which gives the method to solve the critical section problem, they have to satisfy these three requirements. Among these three, these two should be mandatory. Okay, this is optional. Okay, now let us see. Now, this Peterson solution is a simple software solution. Software solution is a code. Okay, that means it doesn't require any of the special hardware. It doesn't need any special hardware. It's just a simple code. With a simple code, it will implement the solution for the critical section problem. Now, this method uses two variables, and those two are the shared variables. Those two shared variables are, one is an integer variable we'll call term. The name I give as a term, int term. Another one is a boolean array. That name of the array we are giving flag, and this array size is just 2. Okay, now these two are the what? For the shareable variables. Okay, these are shared variables. Okay, shared variable means now these two variables are used by all the cooperative processes. Using these two only, they will check whether somebody is there already in the critical section or not. If somebody is there in the critical section, now other process has to wait until that process is have to leave that. Once the currently running process leaves the critical section, then only another process can enter. Okay, let us see how this Peterson solution implements using these two variables. Okay, now here what is a term? So the term indicates which process term is. Now whose term is to enter into the critical section, because simply we cannot give the permission to everyone. Our operating system has to specify, it has to give, now this is the time to enter the so and so process. Okay, and this Peterson solution is applicable only for two processes. That means now only there are two processes are in the race to enter into the critical section. Only for that case. If more than two processes are there in the race, then this Peterson solution cannot be applied. That is a disadvantage. Okay. Now it can be, it's a software solution, can be applied only when only two processes are in the race. Okay, so at that time we are using, let us say the two process, say let us say I will say Pi and Pj. That means ith process, jth process are in the race to enter into the critical section. Now the term variable indicates whose turn it is to enter into the critical section. Suppose term is equal to I. It indicates this is the time to enter Pi process to enter into the critical section. So when term is equal to I, process J, Pj cannot enter into the critical section. Similarly, when term is equal to J, then at that time, so only Pj can enter into the critical section, Pi cannot enter into the section. So the variable term indicates, so whether it's the term of what? Ith process or jth process, whose term it is. So that's a simple term, whose term it is. Okay, next. The flag variable indicates which process is ready to enter into the critical section and which process is not ready enter into the critical section. And see, not all cooperative process wants to access the same shared data or same resource. Okay, it may be different data it may. So we need to say all processes are not ready. Okay, now which process is ready to enter into the critical section, which process is not ready to enter into the critical section, that will be indicated by flag. Okay, suppose if a flag of I, okay, so now flag is in what? One array flag, and it is having only two fields. Okay, let us take 0 and 1, the index. Okay, now I will assume 0 is for the ith process, for j it is 1. For jth process it is 1, for I it is 0. Okay, now suppose if I say if it is this is 1 and this is 0, means now the I process is ready to enter, Okay, so if it is flag value is 1 because it is a boolean. Boolean means either it should be 0 or only 1. If it is 1 means that particular process is ready to enter into the critical section. If anything is 0, it indicates that process is not ready. In this example, ith process is ready to enter into the critical section. J is 0, so it will J is not ready. It may be what? It may be 0 and 1 also. That indicates what? Process I is not ready, but process J is ready to enter. Or both may be 0. That means both are not ready at this point of time. Okay, later, sometimes we don't know, okay, which may be interested. But right now, both processes are not interested. Similarly, so both the process may be interested now. Both the process may be interested to enter into the critical section. But if both are ready to, that means both are in the race to enter, whose turn it is, that will be decided by the turn variable. Okay, if both are ready, if turn is equal to I, then only Pi can enter into the critical section. If both are ready and the turn is J, then only Pj can enter into the critical section. Okay, now let us see that one through the programming. Okay. This is the general structure of any cooperative process which wants to enter into the critical section. Before any process wants to enter into the critical section, first they have to check in the entry section if already some other process is there or not. Okay, entry section. Once it done its job, it has to come out informing I'm coming out. This is what the exit section. Now, how this entry section and exit section will be implemented by Peterson solution? This is okay. Now, if both are same, just now I know for the two process. Assume now for me now. Assume this is for process I. Okay, and this is for process J. Assume two processes because our Peterson solution can be applicable only for two processes. That means only when there are two processes are in the race to enter into the critical section, then only we can apply Peterson solution. So I have two processes. Assume Pi and Pj, and we know that what? We know that they both will share the two variables turn and flag. Assume initially turn is equal to 1. Okay, and it is an integer. Turn is okay, integer variable, turn is equal to 1. And flag, okay, flag is a boolean variable, so it is having two things, that is 0 and 1 index. Okay, now turn is equal to whom? Turn is equal to 1 initially. Assume initially flag, this is true and this is false. Okay, that means 0 for I process, J for J process 1. That means I is equal to 0, J is equal to 0. Simple. Okay, the index. Okay, now the meaning is what? Now process I is ready. True. Process I is ready to enter and process J is not ready. This is what the initial value, and these are shared variable. These variables are shared by both the process. Okay, now let us say process Pi. Now process Pi wants to enter into this critical section. Before entering into the critical section, first it has to check in the entry section. This is the entry section. These three statements are the entry section. Okay, now what is this entry section? Now once the Pi wants to enter, it makes flag of I is equal to true. Flag of I value is what? 0. Flag of I made it true. Yes, true. Okay, next. Turn is equal to J. Now see, Pi wants to enter to the critical section, not yet entered. Now, what it may assume, see, I want to enter, let me check who is maybe there. See, this can be applicable only the two process. Means, if Pi still wants to enter, it's not yet entered. Who may be entered? Already, maybe process J may be entered or not, we don't know. So, what it will do, it only sets, process I makes, immediately whenever it wished to enter into the critical section, it only made it's a turn to J. So turn is equal to J. So turn is equal to 1. I did. Turn is equal to 1. Next what it do? Now it will check while loop. See how while loop will work. So I think you people know how while loop will work. Okay. So generally while some condition and some statements. Okay. Now, whenever the condition is true, comes inside the loop and it executes all the statement, and again goes back to the condition. And this is, as long as condition is true, it will keep repeating this statement. Now only whenever the condition false comes out of the while loop. Okay, this is the general structure of while loop. Now, but here what I done, see, generally we know that what, for the conditional statement there should not be semicolon, but I have written a semicolon. I have written a semicolon for the while. Why? Because this is something like, see, this is exactly like this. Okay, now while some condition, and here, see, inside the while loop, I have not written any other statement, simply semicolon. That means it indicates once you check the condition, condition is true, comes inside, condition is true, comes inside, and do nothing. That is because there is no statement, it's not doing. Again goes back to the condition. Again condition true, comes inside, do nothing. Again goes to the condition. Again condition is true, comes inside, do nothing, go. Now when it comes out of this one, only it comes out of this one when it is false. So as long as condition is true, control is stuck in this loop. Okay, it will keep rotating here. Keep rotating means stuck in the while loop only. So same concept here also. Now check, while flag of j is equal to 1, flag of j is equal to 1, false. False means what? Now flag of j is not ready to enter. Okay, not enter. That means nobody are in the critical section. Nobody are in the critical section. Now this condition is false. When one of the condition in the while loop false, control comes out of the while loop and now process pi enters. Now who is entered inside this process? Now pi is entered. Pi is entered into the critical section and it is executing. Now when it is executing, assume it takes some time to do all these things. After some, now it is assumed it is executing. Which one? Process pi is doing some operation in the critical section. Then after some time, now this will wake up now. Now process pj, now it is ready to want. That means it to process pj wants to enter into the critical section, but any process before enter into the critical section, it has to check in the intersection if somebody is there or not. Here there is no option because it can be applicable only to the two processes. Either pi should be there or pj should be there. Okay, now pj wants to enter into the critical section, but now already who is there in the critical section? Already pi is there. Now again, now it wants to come out. Okay, now it is ready, it means now flag of j it makes true. Flag of j it makes true means flag of j, now it makes this as a true now. Okay, it does. Next, what? Turn is equal to I. Now again, turn it will what it will makes? Turn is equal to 0 it makes. Turn is equal to 0. Now it will check. Flag of I is equal to 1. Flag of I is equal to 1. True. True means 1. Yes, condition is true. And turn is equal to I. Turn is equal to I. Yes, turn is equal to I. I, because I is 0 now. I value 0. Turn is equal to I only. So that is turn is equal to 0. That means turn is I only. Both the conditions are true. When both the conditions are true, what comes inside the loop? There is no statements, do nothing. Again checks. Again checks. Flag of I is equal to 1. Yes, flag of I is true 1. And turn is equal to I. Yes, turn is equal to 0. 0 means I. 0 for I, j for 1. So turn is I, j, I only. So this condition also true. Again condition is true. Comes inside, do nothing. Again go back to the condition. Again condition is true. Why? Because already pi is there in the critical section. When one process is there in the critical section, this method not allowing this process to enter, it blocks in the while loop only. It stucks in. Okay. Now assume, now it is doing some operation, it keep rotating here only, it's stuck in the while loop, it's blocked in the while loop, it is keep rotating in the while loop only. After some time, assume pi done its job. Okay, whatever it wants to do some operation with the critical section, that is shared data, it done. Now pi wants to come out. So whenever any process wants to come out of the critical section, through exit section, it has to inform to the operating system that saying that I am moving out of the critical section. Now you can give turn to anybody else. Now once it comes out of the critical section, now what it will do? So now it will make flag of I is equal to false. Flag of I is equal to false means now it becomes false. False means 0. False means 0. Now false. Now false. Now become false. As soon as become it false, See, it keeps checking a lot. Now again it checks now. See, flag of I is equal to 1, flag of I is equal to 1. No, now it is false 0. Now condition false. Now it comes out. Now Pj is entered into the critical section because already Pi comes out. Now Pj enters. See, at any point of time, anyone. Now assume now Pi is come out. Pi has come out of the critical section. Now who is there in the critical section? Pj is there. Now assume Pj is doing some operation, Pj is doing some operation. Assume after some time. Again what? It wants to enter. Pi wants to enter. Now it makes flag of I is equal to true. Okay, flag of I is equal to true. Flag of I is equal to true. It makes true. True. And then term is equal to j. Now term is equal to j means it makes 1. Okay, term is equal to 1. Now check. Flag of j is equal to 1. True. Term is equal to j. True. Both the conditions true. Come inside. Now it will be stuck in this value. Because this is already there. So once it comes out of this, whenever it makes flag of j is equal to false, whenever it makes flag of j is equal to false, at that time this condition false. Now it will comes out, it will make false. Now there is no thing, now it comes out. Now condition becomes false, now it comes out, again Pi comes. Like that, at any point of time, any one process will be in the critical section. This is how Peterson solution will implement it. Now, since it is allowing any one process, mutual exclusion be achieved. Because any solution has to satisfy 3 conditions, right? That is mutual exclusion, progress, and bounded waiting. Mutual exclusion, since it is allowing only one, how? Very simple. Term decides. See, term should be either 0 or 1. Okay, so that means any one. At a time, both the value we cannot store in an integer variable. In any variable, we can store only one value. So it is either should be 1 or 0. Either 1 or 0 means any one will be allowed. So mutual exclusion is achieved. Now, how progress? See, simple, very simple again. Now, whenever any process wants to comes out, it is making room for some other process to enter. So it is making it false, it is not interested, and it is given term only. See, whenever it wants ready, it is making another process term. See, when process I wants, when it wants to comes in, it will only declare that it's a turn to another process. See, this also, this process making turn to another process. So progress is also there. Okay. Now bounded waiting. So here no process is waiting for the long time. Okay. So it is some restriction is there. Okay. So it achieves all 3. Okay. Now Peterson solution is a summary now. Peterson solution is a simple software solution which is used to avoid the rest conditions by allowing any one process into the critical section, and also it achieves progress and bounded waiting. How? This is a simple code. Okay. So how the entry section will be there in the Peterson solution? This is how entry section, this is how exit section. Okay. Hope you people have understood how Peterson solution is used to solve the critical section problem. Suppose if you have any questions, please write it in the comments. Thank you. Thanks for watching.